This is a battery made out of carbon fiber. It was developed at Chalmers University in Sweden, and it's being called the world's strongest battery. Today I'm going to be talking about this study, Unveiling the Multifunctional Carbon Fiber Structural Battery. And the TLDR is that they developed a battery that's highly rechargeable and has structural strength comparable to aluminum. And if that's all you wanted to know, then thanks for watching, hit the like on the way out, and I'll see you next time. Otherwise, let's go a little deeper. So this is a lithium battery that's sitting in the bottom of a car. The lithium-ion battery can hold a lot of charge for how heavy it is, but it is very heavy and it is separate from the structure. And the thinking is, if you can combine the structure and the battery, then you can actually use less energy to run the vehicle. So a while back, people started having the idea of depositing lithium iron phosphate onto carbon fibers. And then those carbon fibers could be part of the structure of the vehicle while producing power for the vehicle. Well, there was a problem with that. The lithium iron phosphate just wouldn't adhere very well to the carbon fibers. A second problem is that when the power would be discharged from that battery, the volume would shrink somewhat. And then when it would be recharged, the volume would have to go back up. And what this led to was the lithium iron phosphate falling off of those fibers so that they would lose capacity. In fact, they were only retaining 47% of their capacity after 100 cycles of use and recharge. On every battery, you have to have a positive electrode and a negative electrode. So to produce the negative electrode for this one, they took these carbon fibers and they imbued them with graphite. They then had their electrolyte liquid that kind of surrounded it, and they coated the whole thing with epoxy. To produce the positive electrode, they imbued the carbon fibers with lithium iron phosphate. And then they followed the same procedure of adding their electrolyte liquid and epoxy to hold it all together. Then between the two, they placed a barrier. And they experimented with a few different barriers. One of them was just fiberglass barriers like this. And then they also used cellulose barriers as well. Now, I mentioned earlier that when a battery runs and when it's recharged, the volume changes. And it's basically because you're moving lithium ions from one side to the other. So when it discharges, they go one way, and when it recharges, they go the other way. And in the process of that happening, you can cause those other things that are built into those electrodes to fall off. So how well it maintains through these cycles of use and recharge is very important for any battery. In fact, that's what determines the life of the battery. So they ran these through 1,000 cycles of charge and use, charge and use. And as you can see, they didn't lose any capacity to produce power. Another good question is, how much current could this battery produce? Well, I looked up the current density on a regular lithium-ion battery, and it ranges from 0.18 to 0.25 milliamps per centimeter squared. Now you'll notice on this, the numbers in the units are different, but right here, the active material is 5 milligrams per square centimeter. So we can take that and multiply it by these numbers here, and we basically get a similar current density. Here it would be at 0.125, and here it would be at 0.25. So the maximum output is about the same. So here are some of the structural properties of aluminum, and specifically what they discuss in the paper is modulus of elasticity. And what that refers to is how much pressure can be put on a material before it starts to deform. Well, in this case, the modulus of the material depended heavily on what type of barrier they were using. The cellulose barrier actually had the best strength. And as you can see here, it's up nearly at 80, actually was at 76 when it started. And then after it was used, after it went through 1,000 cycles of use, it did lose a little bit of strength dropping down to a little bit above 60. And the one with the lowest strength to start out with was the one that had the Wattman fiberglass barrier between the two electrodes. So finally, how does this compare to materials that are currently in use? The structural battery's energy density was 30 watt-hours per kilogram. And for a standard lithium battery, it's 90 watt-hours per kilogram. The structural modulus for this battery was 76 gigapascals, while for standard carbon fiber, it's 128 gigapascals. Another thing I want to note is that this material, this battery, is significantly lighter than a standard lithium-ion battery. So you'd need a much higher volume to produce the same amount of power. So are we going to see cars or airplanes that are powered with this material? I don't think that's very likely. But if we're talking about storing power from solar panels or wind, I think this material is very promising.